Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion. We are talking about the mean speed theorem and how it can be used to explore the distance traveled by a falling object. This is Chapter 9 in a Student's Guide Through the Great Physics Text, Volume 2. You might recall in my last lecture we were looking at figure 9.1, which illustrates how one can use the mean speed theorem to find the distance an object falls during a time interval AB. And it falls the same distance as another object that would be traveling at the mean or the average speed of the beginning and end speed of the falling object. If you want to review that, you might look back at my previous lecture. What I'd like to do now is to jump ahead one page to Galileo's Theorem 2, Proposition 2. And here I'll just read it. He says, the spaces described by a body falling from rest with a uniformly accelerated motion are to each other as the squares of the time intervals employed in traversing these distances. What is he saying here? He's saying if you consider two objects, both of them that are falling, and they're falling for different intervals of time, then one can compare the distances they fall using the time intervals. So if you consider an object 1, which is falling a distance 1 in some time interval t1, and an object 2 falling a distance d2 in a time interval t2, the ratio of the distances goes as the ratio of the times squared. So this provides a way of comparing two falling objects falling for different time intervals. Now what he does in the section below this is explain how this works, or why this works the way that it does. So let's spend a little bit of time talking about this. First of all, Simplicio explains this using the proof that he says comes from a book he read by the author, and then Segredo goes on to re-explain it in a slightly different way. And so let's look at, this is the way Salviati explains it using figure 9.2, and then Segredo re-explains it using figure 9.3. So I'm going to go ahead and explain this using figure 9.3. Okay, so what is going on in figure 9.3? He says, first of all, let's consider the distance that is traveled by a falling object during the time interval AC. So the distance fallen by an object during the time interval AC. Well, you know how to compute that. The time interval AC, it starts out at speed 0 and ends with a speed equal to the line segment BC. So the average speed has a magnitude of the line segment CE, and hence it travels a distance computed by the mean speed theorem given by the triangle ACED. That is, I'm sorry, triangle. I meant rectangle. The rectangle ACED. So it travels a distance. We could compute that a distance of one rectangle. And remember, by rectangle, we mean a unit of distance. It's a distance traveled by an object moving with speed EC for a time AC. Okay? Now, what is the distance traveled during the second interval of time, CI? So the distance fallen during the time interval CI, well, that's the second interval of time. Well, it begins with a speed given by line segment BC. It ends with a speed given by the line segment FI. And so the average speed is given by the line segment IN. And so we can compute the distance fallen as the distance moved by an object traveling with that mean speed IN for the time interval CI. So that is 3 times the rectangle ACED, or 3 rectangles. That is the distance traveled during the second time interval. I guess it would be also thought about as triangle, rectangle CINB, which is just 3 of these rectangles. What about the distance fallen during the time interval, the third time interval, that is the time interval given by I0, well, at the beginning of time I0, the speed is given by the line segment IF, and at the end of that time interval, the speed is given by the line segment OP, and so the mean speed is OR, and so the distance the object will have fallen will be OR times the time interval IO, which is just 5 rectangles. So 5 times the rectangle ACED, or just the big rectangle IORF. And likewise, you could do this, you could continue. So for the next line or the next time interval and so on. But you could also sum all of these up and say, well, the distance fallen during the first time interval AC is 1 rectangle. The distance fallen during the time interval AI, that is the first 2 units of time, would be 4 rectangles. And the distance, the total distance fallen during the time interval given by AO, that is that entire time of fall, is going to be what? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9 rectangles. So in 1 unit of time, it falls 1 rectangle. Then in 2 units of time, it will have fallen 4 rectangles. And in 3 units of time, it will have fallen 9 rectangles. Notice then that the distance something falls is proportional to the square of the time. So in 1 unit of time, it falls 1 rectangle. In 2 units of time, it falls a distance of 4, which is 2 squared. In 3 units of time, it falls a distance of 3 squared, or 9. This is precisely what he was claiming, is that the distance fallen goes as the square of the time.